MSR is located in Seattle and still manufactures much of their gear at their SOTO headquarters. You're probably familiar with their backpacking and mountaineering gear, like stoves and tents. What's interesting though is they also make excellent winter backcountry tools like probes, shovels, and saws, as well as ski touring poles for both backcountry skiing, snowboarding, and snowshoeing. Behind their designs are passionate engineers and scientists who strive to create better solutions to the real world needs of backcountry adventurers. Because of this, their designs are simple, functional, and reliable. Their philosophy is to give you everything you need and nothing that you don't, so that you can trust your gear when you need it the most. You can check out their winter equipment at msrgear.com. Last presenter is David Hill. David's a professor at Oregon State University and a National Geographic explorer. For over 25 years, he has studied how water behaves from snowy mountain headwaters to coastal environments. He collaborates with other scientists interested in water's response to climate drivers and works with stakeholders to provide information on water resources. He currently co-leads the Community Snow Observations Project, a citizen science project funded by NASA to improve understanding of our physical environment. His presentation this evening, Pacific Northwest SnowPack, What's Changing and How Do We Know? We'll take a look at how we quantify and measure snow, how we detect changes in snow, and what variables matter the most. Thank you for joining us, David. I'll turn it over to you.
Okay. All right. So hello and good evening. It's great to be here, even if here, I guess, basically means my office where I'm alone. So I'm happy to be presenting at this year's virtual NSAW, and I would like to thank NWAC for making this great event happen during the ongoing challenges of 2020. So thanks for being here. So before I get started, let me tell you what this talk is not. All right, I am not here to talk about 2020, 2021 snow. You'll have to wait for Nick Bond's excellent presentation on Thursday, the 29th, if you want to hear about that. So what I am here to talk about is changes in snowpack over the past few decades and likely changes that we will observe in the future. To get started, let me say a few words about the various ways in which we get information on the snowpack. We can directly measure the snow with in situ measurements. We can remotely sense various properties of the snow, or we can use models to estimate properties of the snow in areas where we actually lack measurements. So properties of the snow that we might be most interested in typically include depth, snow water equivalent or SWE, and also vertical structure of the snowpack. So water equivalent or weight measurements are most commonly done in situ. Remote sensing of water equivalent is a developing field, and a lot of current research, which is funded by NASA, is working towards developing satellite assets that can reliably measure SWE. Until then, though, SWE is usually measured with a coring device, which you see here, such as a federal sampler. Or sometimes it's measured with automated snow pillows. And snow pillows use a fluid-filled bladder to essentially measure pressure and therefore the weight of the snowpack lying above. Now, depth measurements are much easier, of course, by comparison. You just need a meter stick or an avalanche probe or anything like that. You sample a few spots to make sure that you're not hitting a rock, let's say, average those results and call it good. And you get a good depth measurement that way. In some cases, you don't need any instrumentation at all. Okay, so this picture from April 1st, 2015, with then Governor Jerry Brown from California in the middle, was taken at a location that usually has multiple meters of snow present at that time of year. And this is a perfect summary of the nearly non-existent snowpack in the Sierra that year. Now, there are definitely a few ways that I would recommend that you not use for making depth measurements, this being one of them. So in addition to being fairly unsafe, This is also a poor measurement in the sense that all we learn is that the snow is greater than a particular value. So it's not a very well constrained measurement. I want you to note that there are numerous citizen science programs that focus in part or wholly on snow depth measurements. So COCORAS is a very well-known one. It has a very large network of backyard observers who regularly measure rain and snow. And the Community Snow Observations Project obtains snow depth data from backcountry snow recreationists and also professionals who are working or recreating in high elevation areas of complex terrain. Now, in terms of remote depth measurements, all right, remote depth measurements typically use ultrasonic sound waves or laser light. And the principle is quite simple. If the locations of the instrument and the bare ground are precisely known, then the time that it takes for a photon or a sound wave to bounce off of the snow surface and return back to the sensor can be used to infer the snow depth. So these measurements can be made from fixed platform like an instrument tower. They are commonly made from a mobile platform such as a plane, satellite, or increasingly a drone. Now, programs like NASA's what's called Airborne Snow Observatory, or ASO, and also their snow experiment, or SnowX, they use airborne assets to repeatedly map selected domains around the Western United States. The very recent ICESat-2 satellite, which was launched in 2018, this provides near global measurements of elevation. Now, ICESat-2 is primarily focused on polar applications, but the platform does also provide reasonable coverage at mid-latitudes. And by doing repeated transects, it has the potential to provide additional information on snow coverage and also how that snow coverage might be changing. Finally, there are a wide variety of satellite assets that provide visual images of snow cover, or they use various spectral bands to allow estimation of snow cover. So on the left here, you're looking at an image from the Sentinel satellite, and this is the Mount Cook area in New Zealand. And on the right, this is a reconstruction of snow cover that comes from the MODIS sensor, which is carried by both the Terra and the Aqua satellites. Okay, so if we're interested in looking at changes in the snowpack over time, the most important thing to consider is over what time scale. So on the one hand, we have very significant changes from one year to the next, right? Just because last year's snowpack was bottomless doesn't tell you anything about what next year's snowpack is going to be like. And at longer time scales, we can have underlying oscillations that lead to changes in the snowpack. The El Nino Southern Oscillation is a great and very relevant example of that, and has a time scale of 3, 4, 5, 6, 7 years in that neighborhood. Now, at even longer time scales, let's say a few decades, we can potentially have long-term changes in some variable of interest, the snow depth at some location or snow water equivalent in a watershed. So this need for long-term data sets to identify true changes in the snowpack, this really kind of determines which data sets we are able to use for analysis for this type of work. And in the Western United States, we are actually really well situated in this regard. So the National Resources Conservation Service maintains a large network of snow telemetry or SNOTEL sites that continuously monitor snow depth as well as water equivalent. SNOTEL sites have varying periods of record. Many of them came online close to 1980. So it's about a 40-year period of record. Now, in addition to this, there's also a very large snow course network, also maintained by the NRCS. So a snow course is simply a location where snow depth and water equivalent are measured manually. All right, so it's not an automated measurement done every day. And this is often done with a federal sampler. Measurements are typically made only about once per month during the snow season at snow course sites. Now, that sounds bad, there's only once a month, but on the upside, snow course sites have much longer periods of record than SNOTEL sites. Many snow courses go back 100 years. Okay, so it's also worth noting that there are other sources of snow data as well. Many states have their own snow survey programs. Many state departments of transportation collect snow information. NWAC collects a whole lot of snow information, and so on and so forth. But if we're interested in looking at long-term trends, then the NRCS data sets are really our best bet. Okay, so what matters though in terms of quantifying snow? So this is a typical profile of the variation of snow, and the vertical axis could be depth, water equivalent, it doesn't really matter, over a given snow season. So we have an accumulation phase where the snowpack builds, and then a steeper ablation phase where the snowpack melts off more rapidly. Now, the vast majority of studies of snow and snow changes have focused on maximum snow value. And this is commonly taken to be the April 1st value. All right, why? Well, first of all, remember that snow courses typically only have monthly data. So we only have a handful of data points over the course of a year. And April tends to have the maximum value for many locations. So April Fools it has been. The thing is, though, that April 1st snow doesn't tell the full story. So we could imagine that something happens climatically to basically simply shift the snow season back in time or forward in time a few weeks. But the overall profile is preserved. Well, in this case, the snow measured on April 1st would be less. But has there really been a true change in the snow for all practical purposes? It's just been a shift. So a measure of how the snow is distributed over the snow season is also valuable in addition to just the maximum value. So we could consider the number of snow-covered days as a valuable metric. Now, this is not something that can be computed for snow courses because you only have 4 or 5 points over the season. So there are far fewer studies of changes in snow-covered days. Now, if the shape of a typical snow versus time curve like this triangle here never changed, then the maximum snow and the snow-covered days would be all that you would need, and that would tell you everything that you need to know about how things change over time, just looking at these simple geometric parameters. But here's the thing, accumulation and ablation curves can change in other ways as well. So in some areas, warming temperatures and increasing rain on snow events result in a snowpack that kind of comes and goes throughout a snow season, right? There may be multiple maximum snow peaks in the curve, and the whole idea of snow-covered days kind of becomes discontinuous because the snow might go away for a while before coming back. So another useful way of quantifying the snowpack is to essentially compute the area under the curve, like the green hatch marks that you see there. And this kind of gives you an integrated over time view of how much snow storage exists during a snow season. Okay, so let's get some baseline information. Let's start with the major inputs to snow. We're all familiar with these types of figures that show warm, wet conditions close to the coast, drier, cooler conditions further inland. Now, the plots that you're looking at here are for winter values. So we're looking at accumulated winter precip over December, January, February, and then the average winter temperature over those months. And this is for a 1980 to 2010 climatology. Of course, it's the particular combination of wet and cold that gives us the snow patterns that we are familiar with in the Pacific Northwest. So here we clearly see the narrow spine of the Oregon Cascades, and frankly, Washington, it would be nice if you guys would share it a bit more. Okay, we have far less sort of seasonal snow than you do up there. Now, if we're interested in changes, we can start by looking at changes to these major drivers of snowpack. So here from the 2014 National Climate Assessment, we can see that we're basically looking at temperatures from the 1991 to 2012 period compared to a 1901 to 1960 baseline. Now in the Pacific Northwest, we are presently about 1.3, 1.4 degrees Fahrenheit above that earlier 1901 to 1960 baseline. If we look at changes in precipitation, they're a little bit more nuanced. This figure is again showing you results from the period of 1991 to 2012 compared to that 1901 to 1960 baseline. The observed increases in the Pacific Northwest are due in part to the major droughts of the 30s and the 50s. So that makes the baseline period comparatively dry. Studies of extreme precipitation, in other words, how the precipitation is distributed over the year and not just mean values, in contrast to these annual values here, have been relatively inconclusive, to tell you the truth. Okay, so how does this show up in terms of changes to snowpack? I want to show you a couple of sets of results here. So in this figure on the left, I'm showing you over 700 snow course locations, and they're colored by elevation. And you clearly see the lower elevations of the Pacific Northwest, 1,000, 2,000 meters as opposed to 2,000 to 3,500 in the Rockies and the High Sierra. Now, over a 50-year period, I calculated the percent change in the April 1st snowpack at each of these snow courses. In the figure on the right, you see a bunch of small gray dots. These are snow course locations where there may have been a trend, but it wasn't statistically significant. Now, the other symbols are colored according to the amount of change. There is one location there that shows a positive change, and there are 224 that show negative changes over the period of 1955 to 2016. The mean percentage change for the stations showing a loss is roughly about negative 40%. We can do this as well for the SnowTel stations. Now remember, these have periods of record that are shorter. So here I have kept all of the SnowTel stations, about 500, that have data from the period of 1983 to 2016. That's about a 30-year period. And that's only about half as long as the snow course figures. So that means that it's probably going to be a bit harder to pick up meaningful trends. So on the left, what I'm showing you is the percent change in April 1 SWE. 3 stations show increases and 50 show decreases. The mean change for stations that do show a loss is about minus 50% over that time. On the right, I'm showing changes in the storage of snow. Remember, that's the area underneath the curve of the snow profile. And there are some differences. For example, in Utah, we saw a lot of reduction in April 1 SWE, but we don't see much reduction here in snow storage. And this may be due to the fact that the snow is on the ground longer. So when we integrate under the curve, things do okay. In Oregon, we see fairly minimal loss of April 1 SWE, but we see greater loss of snow storage. And this is likely due to a shorter snow season. So the take-home message, though, is that with both the SnowTel and the snow course data, there are not a lot of blue markers on these figures. So that's all looking backwards in time. What can we say looking forwards in time? That's a good question. Hasn't happened yet. Don't really know. For us to estimate what is most likely to happen with future snow, we have to turn to computer models. Now, SnowPack models use weather data as input. So for us to model future snow, we need to know something about future weather. And there are many scenarios that have been modeled with regards to future weather, and they all differ based upon assumptions of emissions of greenhouse gases. So we could model future snow under optimistic, medium, or really pessimistic conditions, so to speak. And we could also model things for different times. We could model out to mid-century, we could model out to 2100, and so forth. And on top of that, there's a whole bunch of different weather models out there. So what we really want to do is to sort of do these types of tests with a bunch of different models and kind of consider an ensemble to sort of see what the mean results look like. So as an example, if we consider a long range, so this is basically 2070 to 2100, estimate under a pessimistic emissions scenario, we see large increases in temperature, okay, broad increases across the region, 3 to 4 degrees centigrade in mean winter temperatures. We also see increases in winter precipitation. Okay, so that's kind of a bad news, good news answer, right? And that's very typical of maritime mountain ranges where elevations are comparatively low and temperatures are comparatively high when we compare this to continental ranges. Now, if we look at actual changes in precipitation as snow, so that's what this figure is showing, and everything is below 0 here in terms of these are all reductions. And we see significant declines. So this highlights the vulnerability of Pacific Northwest mountains where our freezing line elevations are high compared to the elevation of the terrain. Now, the dots that you see in these figures are ski areas. And if we pull the results of these locations, and if we zoom out, all right, we can compute the future precipitation as snow. And again, this is end of century pessimistic scenario. And we can see how this compares to the historic average. Now in the Pacific Northwest, okay, so things may not look great, but they could be a lot worse. All right, if you look at the mid-Atlantic and the Northeast states, these are the areas that are at the greatest risk. Now the upper Midwest, like Minnesota, Wisconsin, and so forth, and Rocky Mountain states prove to be the most resilient to these changes in precipitation and temperature. And that's because a few degrees of temperature increase are more easily absorbed in locations where we already have extremely cold winter temperatures. So I don't have all the answers, but in closing, we are very fortunate in the United States to have a lot of snow information available to us. We have historic data, we have current data, we have nowcast estimates from operational models of what the snowpack looks like right now. No one of these sources is the best. They're all different. They have pros and cons, and we should constantly sort of review and evaluate a portfolio of snow information as we seek to educate ourselves about past, present, and likely future snow conditions. So thank you for your time. As you plan your winter season, stay safe, stay informed. And by the way, I will care, I promise, if you telemark. Thanks very much.
Thank you very much, David. So do you telemark, David?
I telemark and AT.
Oh, you do? Oh.
I don't snowboard. Terrible at snowboarding.
Awesome. Well, we've got just a couple minutes. I field a couple of questions here. We've got one. What oscillations are important for impacting the shape of the upper level winds here, I guess in the Northwest, and upstream over the course of multiple years and decades?
Oh, I'm going to punt that to Nick Bond. He's your guy to talk to about that.
Perfect. And
Yep.
I can't remember the schedule, but I believe that is the last night. I think
you have him, I think,
the
yeah.
29th, maybe.
Absolutely.
Nick Bond is the Washington State climatologist who will be giving a seasonal outlook.
And he will give you all the information you want to know.
Nice. That's awesome. Oh my gosh. Couldn't quite interpret that question right away. Well, perfect. Let's see here. Got one from Gregory on glaciers. How do long-term forecast bode for the glaciers at high elevation, like on Rainier or Baker, where the elevation is similarly high to Colorado? Any thoughts there, David?
I don't, I've done a fair bit of work with SnowPack and ice modeling up in Alaska. So we've done some studies of the recession up there, but I actually haven't directly done those studies in Washington itself. So there are other people that would specialize in the mechanics of glaciology that would do a better job of answering that.
Mm-hmm. Yeah, and one of the other questions I was thinking as you were talking, which was an awesome talk, and not super optimistic. Is there any like research in showing how the snow line is creeping up specifically? I mean, that is something anecdotally that I've been noticing over the last several years of skiing, that just seems like the snow line over, decades long trends, it seems like, is slowly creeping upwards. And it seems, especially in this lower elevation maritime mountain range that we have,
so there are some quite a few modeling studies where people have sort of run snowpack models over a variety of areas, and one of the things that they sort of try to do is to kind of, you can sort of think over a particular area, kind of keeping track of how much of that area is covered by snow as a function of the day of year. And then as they model that from year to year to year over like a 30-year period, yes, they can sort of quantify kind of the mean elevation where snowpack is at, or the reduction in snow covered area. Those are all modeling studies, right? And so those have to be sort of validated with data. What I don't know is, I actually would love to look into this, is if the MODIS data sets are long enough to actually look at that with direct satellite data, because that would be, I think, a more convincing thing to do. And those they're getting up to 15, 20 years of data, so that if somebody hasn't done that yet, that's waiting to be done.
Yeah. Well, hopefully someone listening here will get on that. Well,
by
awesome.
the way, so like the one thing that goes along with that is, the tricky thing in a place like the Pacific Northwest is that in the wintertime, of course, the significant cloud cover does make the ability of MODIS to pick up data much more difficult. But the NASA team that runs the MODIS and also the VERS projects, they are constantly coming out with new snow products, and they are about to come out with a new one that does a much better job of kind of filling cloud gaps in the data sets. So what this means is using various algorithms, whereas you might have like 10 days where you previously had no data whatsoever, they're going to be able to infill that with reliable estimates of snow cover.
Interesting.
Yeah.
And, real quick, are you seeking citizen scientists for any active projects? Do you have a link or we can send
Yeah.
out?
So like I said, the two that I mentioned are great ones to look at. The CocoRaz, and it's just cocoraz.org, and then also communitysnowobs.org. They both kind of do similar things in terms of collecting snow data. CocoRaz collects other data as well. It's really a different sort of target audience. So programs like CocoRaz get a lot of school participation. They get a lot of just backyard observer types where people, go out and literally go out in their backyard and measure snow as it falls. The CSO project, we are looking for and rely on people who are traveling to higher areas, who are at higher elevations in areas of more complex terrain. And then we use that data and actually we pull that into our very high resolution models of a number of areas in the Pacific Northwest.
Awesome. And it looks like Renee's just shared both links there. So for everyone listening, if you're interested in getting involved in those programs, the links have been sent out in the chat. So with that, thank you so much, David, for
Thank you very much.
talking for the talk tonight, and have a good evening. All right. So that about wraps up the first night of NSAW's 4-part series. Just a quick reminder, you'll have access to the NSAW raffle until Thursday, October 29th. I'd like to say thanks again for MSR to sponsor this evening. And then, of course, to all of our sponsors for the series, including the AAA A3, I should say, and their grant. And thanks again to all of our presenters for the evening. This was awesome. It's a great way to kick off the season, get our minds thinking about the backcountry. And so we hope to see you all again Thursday, 2 days from now, October 22nd, same time, 5 p.m. That'll be our second session. And I'd also like to thank again the staff of NWAC that made this happen. Molly, Renee, and Charlotte for all of the programming and technology and ticket sales. And, I just want to say we had some challenges with our ticketing platform. We tried a new platform this year. So thanks to all of you who were patient and bared with us as we were exploring the ticketing platform. And so, with that, I'd like to say have a great night, and we will see you all on Thursday. Good evening.